Hello everyone, I'm Pratap here, and today I will take you through gamma distribution, Poisson process, memoryless property, and exponential distribution. This is a very important topic, how exponential distribution is linked to gamma distribution, a Poisson process is linked to gamma distribution, and how to use memoryless property. All the benefits you will get today if you attend the class. Let's get started. This is gamma distribution probability calculator. I'll take you through what is gamma distribution, but you see here, there is one shape parameter. This parameter you have, I've taken two here. There is a scale parameter. This is one here. Not only in this paper, CS1, it will come in CS2, it will come in CM2, and it will be everywhere whenever you work also. So listen carefully. This is the graph here. This is positively skewed. This is a positively skewed distribution. Now, if you see here, see the shape here. So if I make it instead of 2, I'll make it 3 here. This becomes like this. So what will happen is slowly, if you make it suppose 5, the shape is changing, shape parameter. Okay. So it will be like normal distribution. If you make it shape, suppose for example 8, give the shape, and this is scaling, scale parameter. Okay. These are the two parameters here. But importantly, this graph you can do always. And how the graph changes now, I will keep it 3 and then I will change it to 5. You see how this graph changes, like 0.5. More the parameter, in parameter statistics, you have more flexibility. Now 1 factorial, that is equal to 2. 4 factorial, 24. How about 1.5 factorial? We never heard of 1.5 factorial. If you draw the graph of factorial, 1 factorial you have here, the value is 1. So 1, 1, this point is here. How about 2 factorial? 2. So you will come here, 3 factorial, that is 6. We'll try to approximate this one with a graph. This is not a mathematics or statistics class. I'm not going to that. Remember, from this mathematical function, we'll go to gamma distribution. This is called gamma function. So instead of using the factorial, because these 1.5 factorial kind of thing will be needing in probability, we'll extend this factorial notation, and that will come through gamma function. Gamma function, not gamma distribution. We'll use gamma function in gamma distribution. Okay. So let's go to gamma function now. Taking the variable y, it's a dummy variable anyway. It doesn't matter. You write y, z, x. Now if you take alpha 1 here, okay. Suppose you put alpha 1 here, 2 here, then you write alpha 3 here. You can check it. It's a simple integration and just put the values. Then you take alpha 2 here. It will be 0 to infinity e power minus y. Here y power, if you write here 2, 2 minus 1, that will be 1 dy. And again you need to integrate it. To integrate by parts here, integration of second, again e power minus y dy, it will be plus 0 to infinity, 0 to infinity. So if you do that, what will happen is here 1 divided by e power y infinity, that will not contribute. You will get 1 here. Will that. But if you write 0 to infinity e power minus y y² dy, okay, 2 times you have to integrate. I mean, if you do it mathematically, integration by parts, but this will be y divided by e power y, 0 to infinity you need to put here, and this will be e power minus y. Again, you have to integrate. So e power minus y by minus 1. So this will be 1 by e power y. And minus 1 is here anyway, so let me write here. Instead of writing minus 1, I will change this. So if you put 0, e power 0, 1, 1 by 1, so this will be 1 minus this will be 0. You got it? So if you put infinity here, the infinity divided by infinity is there. Okay, that way you have to use L'Hopital's rule. You have to differentiate this one and differentiate this one, then you have to put the limits. If you put 0 anyway, it will be 0. If you put infinity, differentiation is 1, 1 divided by e power y. If you then put infinity, then e power infinity will be infinity, 1 by infinity will be 0. So this will not contribute. So gamma 2 is 1. We need two results here. N is equal to n minus 1 factorial. You will get it. Second one will be gamma alpha minus 1. Suppose I want to find the value of here I want to find the value of gamma 3 here. That will be 2 gamma 2, and this will be, if you put 2 here, gamma 2 will be equal to 1. Apply the same formula. Twice you will get it. Write gamma 4 here, you will get 3 gamma 3. Again 3 gamma 3 I got already 2 here. So I'll write 2. Gamma 3 I got this value. So I can replace here. So that will be 6 again. So I'm getting all these 3 factorial, I mean gamma 3, gamma 4, gamma 5, all these values I can get here. Because gamma 4 I got 6 already. This will be 24 BC. Suppose I will directly like this way. I'll write gamma 3, that is 2 factorial, that is 2 anyway. How about gamma 4, 3 factorial, that is 6. What is gamma 5, that is 4 factorial, that is 24. Anyway, I'm getting here. So what is the benefit, extra benefit? The extra benefit is here I can apply it for gamma 1.5 also. N is an integer, then only this formula is true. So you can't apply this one because we don't have something called 5.5 factorial. 0.5 minus 1, that is 0.5. We don't have 0.5 factorial. Because you don't have 0.5 factorial, you can't use that one here. So what you need to do is you have to apply this one. That will be 0.5 gamma 0.5 gamma half. You can prove it directly using a single integration, okay, but its value is square root of pi. What I want to say is, suppose you write gamma alpha formula, so this formula you write, you put half here, then you will not be able to get this value. You can't integrate this. What I want to say is, suppose for example you write 2x, you can integrate it. So if you can integrate it, you write x square, it's over, right? Something like root sin x. You can never integrate it. There is no integration. You can't express in the form of a function. I mean, it's not integrable, we can say, but some approximation, you can directly integrate and write like this. It's not, even you try x tan x. So whatever functions you can integrate and express as a function of x, those are only you must have solved in your 12th class. You're thinking you take first function, second function. No, that way it's not possible. Okay. Similarly, this, if I write y alpha minus 1 minus y dy, if I write this is neither like this nor like this. This is in between. So that means if this is gamma alpha, sometimes it's integrable, sometimes it's not integrable. Again, when I say integrable, it's not in that sense. You will be able to find its value, or you can write in terms of y. Okay, let me write here for what values of alpha you can do. I mean, you can try 1, 2, 3, all integers. So if alpha is 1, then yes, you can find value. If alpha is 2, yes, you can find value. If alpha is 3, yes, you can find value. If alpha is equal to 4, yes, you can find value. Okay. Again, there is a relation I already showed you in the last page. What is that relation? Relation is gamma alpha is equal to alpha minus 1, gamma alpha minus 1. This one also very easily you can prove. You just write gamma alpha minus 1 here integral, and you multiply this. If you integrate once by parts, you will get this one. It's easy. Okay. By virtue of this one, now if you get gamma 0.5 here, that is half, and yes, this is possible. However, what I wanted to say you is, if you try with gamma 0.5 and put here gamma 0.5, you will not get the answer. Okay. You have to, it's a mathematician's work. You have to change it to a double integral. Then you have to do it. Okay. So we'll not do that, but it will be square root of pi. If you try to find this way, you will never be able to do that. This will be y minus 0.5. This is 1 by square root of y, e power minus y dy. You will not be able to do this way. Whatever methods you know by which you integrate, you will not be able to get the answer. So there is a special way. I'm not going to that. That's a mathematics thing. Okay, leave it here. Just remember this value, this way you will not get, but it will be square root of pi. And by virtue of this, you can now find 1.5, 2.5, 3.5, that way. These are the values you know. For other values, if you want to find gamma alpha, those will be approximate values, and there are so many ways people are trying, but yes, this is a mathematics work. I'm going here once again. This way, here you have gamma 1.5, and then I can write gamma 3.5. So this will be 1.5 gamma 1.5. This is 2.5 gamma 2.5. So this is anyway zero point 0.5 square root of pi, right? This will be 1.5 and this is already there 0.5 square root of pi. That way you write, you will get all the values. So whatever I taught by now, let me list here. So what will happen? You just remember this much, that is sufficient. Up here, you know its value square root of pi. If I write 1 here, you know the value. If I write 1.5 here, then you know the value. This is 0.5, 0.5, gamma 0.5, that is square root of pi. How about this 1.5, 1.5, gamma 1.5, gamma 1.5 I have here. So you write 0.5 square root of pi. So these values I know. 3/2, these values I know. What about gamma 1? Gamma 1 is 1. What is gamma 2? Gamma 2 will be again 1. Okay. So what is gamma 3? Gamma 3 will be equal to, that is 2 factorial, 2. Gamma 4, 3 factorial. So these are the values we know. Okay. These are the values we know. We'll be able to use these values. These are the values we know for gamma function. Now we are doing gamma function. From gamma function, we'll go to gamma distribution. Okay. And also a Poisson process. You need Poisson distribution. These are the things we'll try to learn in today's class. Let me go ahead. So we'll be needing only one thing here. Gamma function value, the integral, whatever integral I have written, that one we'll use. Now let me introduce gamma distribution. Then we'll connect it to a Poisson process. That is what you need to learn. Distribution. And you try to remember the density function. Here the density function is f of x is equal to, this is exponential lambda e minus lambda x. That way you can remember x power alpha minus 1. Here you make it lambda alpha divided by gamma alpha. This is the density function. I already showed you the graph is like this. So when I say positively skewed, you need to remember positively skewed. This is very important. In interviews, you will be asked positively skewed. What is the meaning of positively skewed here? Positively skewed means there is a long tail, positive side. The long tail is towards the positive side. You see, this is positive side. If I write this is 0, infinity here, in this direction, if you see that there are high values have low probability. Even in Pareto distribution also, what will happen is these are the distributions gamma, Pareto, these are positively skewed. A lot of positively skewed distribution we use in our modeling work. Positively skewed. Beta distribution is the only one you will see which is negatively skewed. So that means this probability is very high as compared to this probability. So better I will show you this way, because point-wise concept is not there in continuous. So this probability that someone gets 5 lakhs a month as compared to someone gets 50,000 a month. There is a difference. This probability. Okay, if you see the height, so this probability is very high. This probability is very high as compared to this probability. So for the time being, because we are not doing any modeling here, statistical modeling or actual modeling work, I am keeping it here. We'll do it in CS1 also, in CS2 as well, because it will come time and again. Just remember it's positively skewed. Skew means long tail. That is toward the positive side. Done. And this value you know. You can check that the total probability is 1. This total probability here, that is equal to 1. So simple mathematics, if you sum up all, this should be equal to 1. You can check it. Okay. How can you check it? This is 1. 0 to infinity. You write everything. Lambda alpha e minus lambda x power alpha minus 1 divided by gamma alpha dx. If you integrate this one, you should get 1. It's very easy, because what I will do is I will take lambda alpha and gamma alpha outside, and here lambda x I will take y, e minus y. I've taken y is equal to lambda x. That means my x is lambda divided by y. Then here if you see lambda power alpha, I've taken out. So 0 to infinity once again. And dx I will find from here. dy will be equal to lambda dx. So dx will be dy divided by lambda. So what will happen? This lambda, that is lambda power alpha, I can cancel with this. And here lambda gamma alpha. Okay, let me write gamma alpha here. 1 divided by gamma alpha 0 to infinity e minus y power alpha minus 1 d y now. So if you remember, I've started with this one, and this is exactly gamma alpha. Even before the distribution, gamma alpha was there. Because the total, this probability, we wanted a function like this to make this as a density function, because this sum of all the densities must be equal to 1, right here, 0 to infinity f of x dx. That's where we got this gamma alpha. Anyway, they're equal. Now we can cancel this one, and this one, because this is nothing but gamma alpha. So you get 1 here. Okay, this is something you need to remember. If you have started, then you need to find the value of Ex and variance of x. Ex you need to remember here. This is also quite easy. You just need to write x f of x dx, and this will be alpha divided by lambda, then alpha divided by lambda square. Although you will not get a derivation, but sometimes when you are solving a problem, this is required. So let me write here f of x is e minus lambda x power alpha minus 1 divided by gamma alpha. So here what will happen, remember, anything you need to integrate between 0 to infinity. For example, if I try to integrate 0 to infinity, lambda is anything, okay, alpha is anything. These are the parameters. Again, the significance of the parameters you will be able to know after few days when you really try to understand the subject rather than studying in a mathematical way. Now we are doing mathematics because this is the initial stage for you. Here x positive. So if you see here lambda and alpha and e power minus lambda x, anything you write here, suppose I will write a star here. Okay, I will write a star here and I will write a square here. Then what will happen if I write e power minus star here, x, and x power alpha. Alpha means again matching with square. Square minus 1 divided by gamma alpha. Alpha means again square. If I write this, if I integrate, it will be equal to 1. That means anything if you write here, anything, just anything. Let me replace it by these two values. Let me replace by 3 here. Wherever star, I will write 3 here. Wherever star, I will write 3. Wherever this, I will write 5. 5. And these are the values when you do practical modeling from the data, you will get these values, you will estimate from the data, whatever data you get. From the data only these values you will get. That is only statistical modeling. But now just remember, any values you put here, this will be equal to 1. Even what I will do is, if I put here lambda, in place of lambda, I put 2 lambda, 3 lambda, lambda square root of lambda. I can write anything, no problem. Suppose I will write lambda plus 1 here and alpha minus 1 here. Then also it will work, because lambda plus 1 is another constant. That could be lambda dash or maybe any other variable a I will write here. Then alpha minus 1 I will write b. Then e power minus lambda x. Lambda is my lambda plus 1. Then x. Lambda plus 1 I have taken a, right? So let me write a. A power b I have written. Then e minus lambda x. E minus lambda x. Minus lambda is minus lambda plus 1. I have taken a already. So I'll write this one minus ax, x power alpha minus 1. Alpha I have taken my alpha minus 1, minus 1. That way, divided by gamma alpha. And my alpha is alpha minus 1. This will be also equal to 1 if you integrate this one. Alpha minus 1 I have taken anyway this a and b. So you can replace it by b and b. This will also be integration. I mean, if you find the integration of this, that will also be 1. Okay. So why I'm saying all this? This is what you will see in most of the problems. What will happen is, if I want to find Ex here and EX square here, from which I will be able to find variance of X. Now to find EX and EX square here, EX will be equal to X f of X dx. So if I want to find this value, X I need to multiply. So what will happen? In place of X alpha minus 1, I will have X power alpha. Okay. But I have to make it alpha minus 1 only because I want minus 1. So I'll write this way, dx. This x I have to multiply with f of x. But other things are the same. Lambda power alpha, e minus lambda x, and gamma alpha, everything is same. So what is changed? Everything is same. What is changed? I multiplied x. So this became here, x I multiplied here. Acha, this will be alpha. So I'll write alpha plus 1 minus 1. I multiplied x to this one. So it became x power alpha. I wrote x power alpha plus 1 minus 1. So if you make alpha also alpha plus 1, let me erase this. Now what I will do is 0 infinity. Now this alpha I will make alpha plus 1. So I will multiply with this. This will become alpha plus 1. Already I have alpha plus 1 here. This is my new alpha or whatever beta you write, dx. Then I want here alpha plus 1 also, lambda alpha plus 1. I multiplied by lambda, so I will divide by lambda. Then what I will do, I will write e minus lambda x. Then what will happen? This alpha plus 1 will be my new alpha. This is my new alpha, this is my new alpha, this is my new alpha. Okay. If you want to replace it with another alpha or alpha dash, whatever you want, lambda power, you write a here. E minus lambda x, x power a minus 1 divided by, I will write this one is alpha, this expression is alpha plus 1, this. So this I have taken already a, so I will write a here, and this lambda I will take it out. This alpha I divided here, so I have to multiply it. So this alpha by lambda I will take out. This alpha by lambda I will take out. And this is 0 to infinity dx. So what will happen? Alpha divided by lambda, this will be equal to 1. Because this is density function of gamma alpha here replaced by alpha plus 1, that is a. Lambda is not changed. We don't need to change lambda here. Okay. So what happened is we have two parameters. The two parameters could be anything. Okay. According to our requirement, we have written alpha plus 1 lambda. Alpha plus 1 is my a. So I got alpha by lambda. You can use a similar way to find EX square as well. So let me write now EX square. To find EX square, I will write once again f of x lambda e minus lambda x power alpha minus 1 divided by gamma alpha. This is my f of x. So now I will write EX square. EX square will be integration x square f of x dx. Then what will happen? X square when you multiply, this will be e minus lambda x power. So this will be alpha plus 1. But anyway, I need to keep minus 1 here. So when I write 2 here, x square you multiply, this will become alpha plus 1. Right? So we have to change it to alpha plus 2 minus 1. Now final value will be, I mean this minus 1 I will keep. This 2 I brought here. Now what I will do is, I will make it this one alpha plus 2. So how I get that? Alpha plus 2 gamma function will be alpha plus 1 gamma alpha plus 1, and this will be alpha plus 1, this will be alpha gamma alpha. So this will be alpha alpha plus 1 gamma alpha. So I need to multiply with this alpha alpha plus 1. So what I will do is, I'll write 0 infinity, then here I will multiply alpha alpha plus 1 to gamma alpha, and then I will write this. Here also I will multiply alpha alpha plus 1. So this part is over now. So I got this denominator, and this numerator anyway I have alpha plus 2 minus 1 dx. Everything is fine. I didn't change lambda x, so lambda x will be as usual. However, I want here also lambda power alpha. So lambda power here also I need alpha plus 2. Here also I need alpha plus 2. So I had lambda power alpha already. So lambda square I need to multiply here. Next step, if you see, let me erase all this. Next step, if you write it here, you take alpha alpha plus 1 divided by lambda square out, everything, and within you will get whatever you want, and this will be the density function of gamma alpha lambda, alpha plus 2 lambda. See, everything we have. I have alpha plus 2 here, and I have lambda power alpha plus 2 here, and e minus lambda x here, x power alpha plus 2 minus 1. So exactly this is the density function of this gamma distribution. Because this is the density function, if you integrate, the total probability must be equal to 1. So this is 1 anyway. So my answer is, my final answer, alpha alpha plus 1, alpha alpha plus 1 divided by lambda square. I got my Ex alpha divided by lambda. I got Ex square alpha alpha plus 1 divided by lambda square. Then I will find variance of x. That will be Ex square minus Ex whole square. That will be equal to alpha alpha plus 1 divided by lambda square. This minus alpha square divided by lambda square. So if you cancel this one, you will get alpha divided by lambda square. This is your variance of x. Even if you don't want to do this way, in the next chapter, we'll study moment generating function. There is another way you can derive all this. This is the minimum required. That is why I explained all. Now, we'll go to the conceptual part. One is e power minus t. Okay. Let me write e power minus t. This is memoryless component. So, e power minus t, if you see, if you draw the graph, it will be a decreasing graph. This gamma distribution is linked with Poisson distribution as well. Now, there is a direct link between gamma and exponential also, because exponential is a particular case of gamma distribution, and gamma distribution, you can say this is a generalization. I'll give you several examples now, because this is important. Here, f of x, two parameters, we write like this: gamma alpha lambda, lambda e minus lambda x, x power minus 1 divided by gamma alpha. This we know. Now, you can get chi-square also, Erlang distribution also from here, but I'm not going to those now. Exponential distribution here, when you take a particular case, what will happen? Let me write alpha is equal to 1. My f of x will reduce to, when I take alpha 1, this will be lambda e minus lambda x. This will vanish. Vanish means not vanish 0, it's 1. This will vanish the power, and this 1 if you put, that will be 1. So it's very simple, lambda e minus lambda x, and let me write mean variance as well. EX and VX. Alpha divided by lambda, alpha divided by lambda square. These are the mean and variances. And here also we know mean and variances. Now I'm not interested here. So let's talk practical applications. Okay. Suppose you consider a bulb, lifetime of a bulb. So what will happen when we talk lifetime of a bulb? This is bulb, okay, or you have a bulb like this as well, tube light we say, right? So in these kind of bulbs, what will happen is the lifetime, okay, we'll start from bulb, then we'll go to waiting time. So the lifetime of this bulb follows an exponential distribution. This means what? This means suppose you have a bulb and already you used it for 1 year, 6 months. You just think it, you can relate it with your daily use. Then the lifetime of a bulb will not change. It will remain the same. Because how the bulb we use that get damaged, we say fuse, how it fused actually. There is a random thing. Sometimes you get a lot of voltage, sometimes something happens, right? So due to that factor, the lifetime, after some time also, the probability of the probability of the bulb's lifetime never affected, right? Mathematically, if I write this way, this side let me write, I'm connecting with this. The probability that the lifetime of x is lifetime, suppose x follows exponential lambda, x is greater than s plus t given. This is called memoryless property. X is greater than t. Mathematically, you can prove it. Probability x greater than s. This means what? Again, we'll go to waiting time for this as well. Now, this means actually the probability that it will glow another s seconds or s minutes or s years, at least s units at least, is equal to this probability s plus t. That means what? This time already you use, it's not affecting. Mathematical, so you can prove. How we prove actually? We find probability x is greater than x here from this one. And if you do this one, 1 minus this, if you do it, you will get 1 minus e power minus lambda x. I mean, this is a very small one. Just find 1 minus this. If you do, you will get this. Because probability x is greater than x is 1 minus probability x less than or equal to x. And probability x less than or equal to x, you can find it. Or you can directly integrate x to infinity, this one here. This is 0 to infinity. Okay. You will, from this one, you will get this one. This is f of x. Now, if you put here, sorry, this is less than or equal to x. This is my probability x greater than x. So if you put it here, if you put this function here, this left hand side is e power minus lambda s plus t, this probability minus lambda t, and right hand side is e power minus lambda. Mathematically they are the same. But what is the meaning of this? This means memoryless property. So where you have memoryless property, you go through all the distributions, you know. This distribution, exponential distribution, has memoryless property. That means when you talk about lifetime of a bulb, for example, it doesn't matter it's a new one or you already used for 6 months or 8 months, it doesn't matter. The probability that it will fail, it will not glow, the probability that it will get damaged, that will not change, that will remain the same. So you can use gamma also here. It's not that we use always exponential. Sometimes what happens is there are many different ways. Okay, if you think that, already I said you, the more parameters, the more flexibility. Suppose you are staying in an area, there are different ways it can affect. Okay. You bring more factors like the filament is there within the bulb. Okay. That also can tear with time. So all those things, if you bring more variability here, then you have to use another parameter. Even gamma is not the final one. From gamma also we can go to 3-parameter family, 4-parameter family. Gamma, this gamma we are using here, we have 2-parameter family. Anyway, now this is the concept of a Poisson process. This is 0, this is 1, 2, 3, 4, 5, 6. That way I will write. Now this is Poisson process. From Poisson distribution to Poisson process. What is Poisson process? If I write a Poisson distribution here like this, Poisson lambda, it will give you the values, probability x is equal to x e minus lambda, lambda power x divided by x factorial. If you see here, it has no time dependency here. And we take a time, okay, constant time, 1 hour or 2 hour. Within that, we say lambda is the rate. Okay. Now here what will happen? This is your static one, Poisson distribution, no time dependency. When you say Poisson process, then what will happen? Instead of this one, we'll use x here, x. So x will make a time dependency, that is t. Sometimes you write n also, doesn't matter. You write x or n. So this is x0, x1, x2, x3, x4, that way. So here, suppose you start from 0 Poisson process. At 1 it goes to 5, at 2 it goes to 10. That way it will increase. Okay, Poisson process, it's a counting process. Then with time you get more and more claims. But I've taken constant rate 5. So here x0 is the random variable here, x1 is the random variable here, x2 is the random variable here, x3 is the random variable here. You get 5 claims in unit time. Time is suppose 1 day. Every day you get 5 claims. Again, Poisson process means the claims you get one claim in one interval, the other claim in another interval. They're independent. Independently you will get, and you don't get claims in bulks. You get either zero or one claim during a very short time interval. The probability of getting 2 claims is more. Again, I mean, these are not important here. Just I'm uh, writing this because we'll use this one here. Suppose this is the time you get your first claim. This is the time 0. Suppose you get your claim here, one claim here, and second claim here, 2 claims here, and 3 claims here. This waiting time, if this follows xt or nt, whatever you write, normally we write nt like this, or sometimes nt. I mean, in different material, you see differently, or xt, whatever you write, it doesn't matter. Okay. NT follows Poisson lambda t. Here you got your first claim. This is first claim. Second claim. Don't compare with this diagram. This diagram is different. This is 1, 2. This is the rate. Here I'm talking about claim. So this is your first claim. Like see here, this is, if you compare with this one, this is my first claim. I got my first claim here. This is 1 according to this diagram. This is my first claim. This is my second claim. This is my third claim. So what will happen is, this notation is the waiting time. Okay, waiting time till I get a claim. Suppose I'm waiting for my students to start my class. T0 will be the waiting time to get my first claim. T1 will be the waiting time to get my second claim. All the waiting times, they follow exponential distribution. And exponential distribution with the parameter that is with this one, lambda, the same parameter. So here I can write T0 follows exponential distribution with parameter lambda. T2 follows, T1 follows exponential distribution with parameter lambda. T2 follows exponential distribution with parameter lambda. Like that, I will write T alpha that will follow exponential distribution with parameter lambda. So instead of finding the waiting time to get the first claim or my first student or first event, you can say, if I wait to get up to alpha events, what will happen? You add everything. If you add everything, all T0, T1, T2, T alpha, that will be my waiting time, the total waiting time. So that way what will happen? The total waiting time will be this. Suppose X is my total waiting time. That will follow here. I have not taken X here, so don't get confused. I have taken NT. So my X will follow gamma distribution with parameter alpha and lambda. So when I talk about waiting to my first claim, first event, that is exponential. If I wait till getting 5 claims, that is gamma. Similarly, suppose I'm waiting. I'm working in the government department, and government says you go and wait on that road, and you check that 5 buses they cross that bus stop. Then you come here. So I'll wait. I mean, buses are randomly coming, not fixed time. So one by one coming. So if I wait till first bus, that waiting time follows an exponential distribution with parameter lambda, and that lambda must have been estimated before. If you wait till getting the 5th bus, then that will be your gamma distribution with parameter 5 and lambda. So normally we write alpha and lambda. That is gamma distribution. So that way they are connected. Remember one thing. This is Poisson distribution. That is arrival pattern. So when you count the number of events, then you have to use Poisson. Average number already given, lambda t. That is the parameter. The rate is lambda. Rate means per unit time, whatever unit you can take per unit time. So this is discrete distribution, and these are continuous distributions. T0, T1, T2. These are continuous distributions. And then if you add all here, that will be your x. So let me write here x. X is equal to T0 waiting time. That is exponential. T1 waiting for the second event starting from first, that is inter-arrival times we say. Then T2, this is the waiting time. All waiting times are exponential with same lambda parameter. Up to I added T alpha. That is my gamma distribution. Even there is a mathematical proof using Poisson also, you can prove that one. But what you need to remember here is this follows Poisson and these are exponential. Okay, you have 1 or 2 problems you are supposed to do. And the second particular case of Poisson distribution will be using, that is chi-square distribution. But chi-square will require special attention. I don't want to extend this one to bring chi-square here. Chi-square distribution, T distribution, F distribution, all these need special attention for you. So I'll do it separately in other class. Normal, log normal, beta distributions, all those I'll complete in other class, and then we'll proceed further. For today, class is over.